Okay, so we're, I guess, going to be either missing a few people or waiting for some latecomers, but we can get started with our stuff for today so that you guys will be able to get started on the exercise as early as possible. Like the previous weeks, I guess maybe it would be good to start if there are any questions about exercise 5 or issues with exercise 5. So the one thing that I was going to show you perhaps here is that the CSC notebooks, as you have likely experienced, has been a little bit unstable lately, and there have been times when instances wouldn't launch or things like that. So normally we're using this Intro QG 2019 blueprint. So that's the thing you normally would launch if you're using the CSC Notebooks platform. I've created a second one called Intro QG 2019 Lite. And the difference is that this does not use the persistent storage option. So it means like your files from the last time you connected are not there. And your files are not stored, but it would allow you to still use the instance for 6 hours. So unlike Binder, it won't die. But it doesn't keep your files there, so it's very important to make sure that you're saving your files to Git or using Git to commit them to GitHub, because unfortunately, once the instance disappears, everything goes with it. This option is here mostly for those cases when the file system seems to be having issues with the CSC. They have sent a message saying that, again, it's back to being stable, but that's the second time we've heard that this fall. So it's possible that the file system could go unstable again. I don't know exactly what the cause of it is. I don't know whether we have, between us and the Automating GIS Processes course, I don't know if it's just like that we have a lot of users. But in the event that you need to use that, this extra image is here. And as I've already said twice, I just want to make it perfectly clear that your files will disappear if you allow this image to expire or to be destroyed without saving your files to GitHub. So it's there if you need it, and that's hopefully something we don't need, but it's just good to have a backup plan because obviously we've seen evidence that we might need to use the backup plan from time to time. So, okay, so then what we can do is switch to our lecture topic for today, and essentially there are 3 parts to the lecture. I'm going to present the first one, and then the slides will be available on the web page for the course for the other 2 parts. They're mostly for reference for helping you with writing the final report for exercises 6 and 7. I'll talk about that a little bit as well after we finish with the lecture material. But these are kind of good resources for you to go and have a look at some additional information that might help you understand what you're doing for the final report, or even give you some information that you can cite or references that you could consider citing in the final report. But this week is kind of a shift in terms of what the course is doing, and it's going to be less about converting some equations into Python code like we've done the previous weeks, and more about applying some different equations that we've used previously to understand a topic we haven't yet discussed, and that's thermochronology. So I'm going to give kind of a very general introduction to what thermochronology is, and as is always the case, you guys will probably understand some parts of this, maybe not all of it, but hopefully between this, the extra slides, and the 2 weeks time you have for the next 2 exercises, parts of this start to become a bit more clear. But part 1 is basically just an introduction to what is thermochronology. As you can guess already, it's related to geochronology in a way. So if you've done anything like with geochemistry course or something where you've done any kind of dating methods, this will be kind of linked to that type of that topic. And then the other two pieces, I think I'll show just briefly what the slides cover, but not go through them in any detail, just so you can see what's there. But it's more details about specific kinds of thermochronology, certain isotope systems that are used, and then the last part is more about applications of thermochronology. So it's a big topic. We can't cover it all in one lecture, certainly, but this is just a taste. All right, so as mentioned, the goal really is just to introduce what is thermochronology and talk about one of the kind of essential components of thermochronology referred to as a closure temperature. And we'll define that and talk about what that means. But more or less, this is the basis for the age that you get when you use this dating method. And I guess there's a couple things that are good places to start, or a couple things that are good to consider. First off, why are we dealing with thermochronology at all at this stage in the course? Why are we jumping to yet another topic? Well, we've been looking at stuff that's related to erosional processes, to the way that landscapes are shaped by hill slope diffusion or by river erosion and things like that. And maybe you haven't put all the kind of pieces together separately, but essentially these are all ways in which landscapes are being shaped by geomorphology or geomorphic processes. And thermochronology is one of the ways that we can start to look at those processes over long time scales. So when we say long-term, like tectonic and erosional processes, we're talking order of millions of years. So there are many methods you can use to study erosion over short time scales. You can collect sediment in a river by installing some kind of dam and measure the volumes of sediment that are accumulating and other things like that. But that generally works for only years to tens of years. And this is a method that allows us to go much further back in time to look at how these processes are working over longer time scales. It's also something that is linked to some of the equations that we've seen already, because thermochronology, as you can tell from the name alone, is related to temperature. And we didn't really look at the example of the heat transfer process as an application of the advection or diffusion equations, but essentially when we look at things like calculating temperature as a function of depth in the earth, you can use that as an advection and diffusion equation combined. So these are things that we've already seen. Obviously, we've seen the advection equation in the case of river erosion with the stream power erosion law. Diffusion equation came up when we looked at hill slope diffusion, but these both are used as well for doing heat transfer in the crust. And actually, if you look at the notes on the derivations of some of these equations on the course webpage, you'll see exactly those examples of heat conduction with and without advection. So heat conduction is basically just a diffusion equation. And so we've already seen also the kind of math that's linked to this. Furthermore, we've dealt with this idea of misfits and fitting some prediction to a measured age. So we've done this in the context of the hill slope erosion, where we had the hill slope profile you were trying to fit with the misfit function. We didn't really deal with it too much with river erosion, but we did deal with it again with the glacier and the ice flow exercise. So again, we're going to be dealing with this with the thermochronology data, because often what we have is a measured age that has some mean value and a standard deviation, and we can then come up with a model where we can predict a value for an age and then see how that age compares to an observed age. So we're going to take some data from a few papers, and then we're going to fit our observed ages with the model and see how well we can do. So it's combining a bunch of different pieces of things we've already used, which is why I kind of like this as the last part of the course, because it's sort of a synthesis in a way, bringing together all of the different pieces. So to start, in terms of the thermochronology topic, when we talk about geochronology, we're basically talking about the science of dating geological materials. And in many ways, a lot of the chronometers that are used for thermochronology are basically working very similar to how they would for geochronometers. So if you have something like uranium decaying to lead in a zircon crystal that you're using as a way of dating the age of zircon from the half-life of the uranium isotopes that are producing the lead, we have similar things that happen for thermochronology. We'll see some examples of those. But essentially, it's in many cases based on radioactive decay, accumulation of some kind of daughter product, and then measuring an age based on how much of the daughter product has accumulated. When we talk about geochronological ages, this is basically referring to things like a crystallization age. So it's a sort of an age at which some material formed. And so that's often the interpretation you have, is that if you look at zircon, uranium, lead age for some granite body, often you're looking at the time at which that zircon crystallized from the melt, and then that gives you an age at which the melt itself was emplaced. It's different with thermochronology, and the reason for that we'll get into in more detail, but in general, what we're looking at with the ages here is the time since the material cooled below some temperature. So what it means here is that the age we're looking at is not a crystallization age, it's an age that refers to the time at which the rock cooled below a given temperature. And that temperature will depend on which system of, which kind of thermochronological system we're using. So is it helium in apatite or argon in muscovite or something like that? There's a number of different systems, and they all have different temperature sensitivities. The basic picture looks something like this. So if we want to describe what a thermochronometer system is, we have some parent isotope, so radioactive parent isotope in this case, that's going to undergo spontaneous sort of decay reaction, produce some type of daughter product. So there's going to be some daughter product that could be an isotope. So if it's uranium decay, it could produce alpha particles, which are basically a helium nucleus. And so you could have helium accumulating inside your crystal, or you could have some crystallographic feature. And so in this case, this refers to things like damage trails that can be left when you have fission of a uranium nucleus. So it produces larger charged particles that basically repel themselves and tear a damage zone through the crystal lattice. And so that damage zone can also be used, and the accumulation of those damage zones can be used as a way to measure an age. And then there's the mineral in which this whole thing is happening. So I guess this part about the radioactive decay, that's probably somewhat familiar, right? And using radioactive decay as a way to measure ages, right? We all know that part. The difference here is that we're going to have a little bit of a different behavior, because sometimes our daughter product is trapped inside the crystal, other times it's not, and that is basically a function of temperature. So this will be the kind of big difference. But we've got decay happening inside the crystal. The daughter product may then diffuse. The sort of way in which we apply the data then is to try to link these ages to understand the thermal history of a rock. So this has been used in the oil and gas industry for probably 50 years or more, because there are certain chronometers that are very sensitive to temperatures where oil and gas form. So it's quite a useful thing to know when your hydrocarbons mature. And if you know the timing of that and timing of various other things that are happening in your area, you can get a sense of whether there should be oil or gas present where you want to go exploring. But basically, this science thermochronometry is the application of these ages to try to understand a thermal history. And there's another definition here for thermochronology. I've given all these definitions here just because if you read through some of the articles that discuss some of this data, you'll see these different words, and it's useful to have a kind of specific definition so you can distinguish between thermochronometry and thermochronology, because they're not so different in terms of the spelling, but they mean different things. So thermochronology is basically just this thermal history that comes from the dated minerals in a rock, in some mineral, geological terrain, whatever. And most of the applications that we're looking at, we're trying to look at things like past rates of tectonic processes, rates of erosional processes in the past over generally timescales of millions of years. So we want to use that thermal history to tell us something about how did this rock get to the surface, and what can we say about the thermal history that can tell us about the processes that brought the rock up to the surface. So the key part of this is that we have to link this temperature to some depth in the earth. So if we have a mineral that's sensitive to a certain temperature, 100 degrees C or something, we have to figure out, okay, back in the geological past, how deep in the earth was this 100 degrees C? Because this rock basically records the time since it was at 100 degrees C coming up to the surface. If you can figure out how deep it was at that time, then you can calculate a rate of exhumation from that. And we'll see some examples of that, so don't worry at the moment if that's not totally clear. The thing is, this is not a very easy thing to do in general. There are many, many different thermal histories that can produce the same age. So when it comes time to interpret the data, it can be a bit complicated. And we're going to go through an example with the exercise for the next 2 weeks of using a fairly simple model to predict ages, and on that basis then look at things like rates of exhumation. So yeah, here's the basic essence of the system, and essentially in terms of kind of like end member behaviors, we have basically two things happening. One is the behavior where the system is closed. What that means is that when there's decay of the parent isotope to produce some daughter product, the daughter product is trapped inside the crystal. That's the kind of one end member. The other is that we have decay of the parent isotope to produce a daughter product, and the daughter product is lost and diffuses out of the crystal over a fairly rapid time scale in terms of geological rates. So these are the two different behaviors. The daughter product is basically continuously being produced. You know, with any kind of radioactive isotope that's decaying, it's always producing a daughter product over a certain kind of frequency. But the behavior of the system, whether it's trapped in the crystal or whether it's lost, in this case, is largely dependent on temperature. So it's probably not a big surprise to say that when you take crystals to higher temperatures, rates of things like diffusion inside the crystal will increase. And so daughter products that might be trapped in the crystal at cold temperatures are able to diffuse out of the crystal at high temperatures. So just to say that another way, you can kind of picture the closed system as low temperature and the open system as high temperature. What this high and low temperature mean will depend on which mineral we're looking at, which daughter product is being produced. For instance, the decay of uranium to lead. Lead is a pretty big isotope. It doesn't really diffuse very easily through the crystal lattice, and that's why, you know, one of the reasons why it's a good geochronometer, because essentially the daughter product doesn't really get lost very easily from the crystal. It can diffuse out of the crystals, but it's not a very likely thing to move throughout the crystal because it's so large. Things like on the other end of the spectrum, helium, you know, it's a very small atom and it easily moves throughout the crystal. In fact, because it's an inert gas and it doesn't really react and become part of the crystal lattice, it's very easy to sort of diffuse out of the crystal at relatively low temperatures. So the transformation, or the sort of transition, I should say, from this closed system to open system is not something where there's like a step function. It does occur over a kind of range of temperatures, meaning that at temperatures below a certain value, the system might behave like it's completely closed. Above a certain value or deeper in the earth, it may behave like the system's completely open. But then in between, there is this transition zone that's referred to as the partial retention zone or partial annealing zone, and that depends on whether you have what kind of daughter product you have in the crystal. But as the name would suggest, the partial retention zone means that part of the daughter product is trapped within the crystal within this gray region. So this is a range of temperatures. And again, it'll depend on which system you're looking at, but it could be 50 or 100 degrees temperature range. So it can be significant because rocks generally don't go from super deep in the earth up to the surface. that quickly. So it means that they may spend a bit of time in this partial retention zone, and that can be important in some cases. So yeah, I think I've already said this part here about the trapping of the daughter product and complete loss. So the closure temperature idea was established essentially as a way to simplify this behavior a little bit, because we know that things are more complicated. But if you want to just put a single temperature in there to say, okay, if you're below this temperature, you should basically be keeping all the daughter isotope. If you're above, you should be losing it. You can do that with this closure temperature idea. And it's essentially the definitions given in a paper in the 70s about the temperature of a thermochronological system at the time corresponding to its apparent age. I don't find that to be a very straightforward definition. So I suspect probably you might not find that to be that clear either. But in essence, you can think about it as the temperature where above the closure temperature, you're losing most of the daughter product. Below it, you're trapping most of the daughter product. In this case, it's actually about 50-50. It's right in the middle of this partial retention zone. So at the closure temperature, in essence, we're losing half of the daughter isotope over the time window that's being considered. But the thing that's really nice about this is that once we have this closure temperature idea, we can then take an age, and the age can refer to a specific temperature. So it allows you to kind of link back an age to a temperature in the Earth. Now, it does vary as a function of a number of different parameters. So it's a little bit complicated, as you might imagine, for any kind of isotope-based dating system. Things can get a little bit complicated. So which host mineral you have, which daughter product, the size of the crystal, the composition of the crystal, cooling rate, there's a number of different things that will affect this closure temperature. But in general, it's a very simple concept to allow us to think about sort of trapping versus loss of the daughter product. And this works only for this monotonic cooling. So it means you can't use this definition of a closure temperature when you have kind of reheating of your samples. So it's only for continuous cooling. But that works for a lot of cases where thermochronology is being used. Just to give you an idea of what this closure temperature looks like for different mineral systems, this is the system that's called apatite uranium, thorium, helium. So this is uranium and thorium decay to produce helium isotopes inside an apatite crystal. And this is then showing in the plot here how the effective closure temperature varies as a function of the cooling rate. So how quickly is the sample cooling 0.1 degrees C per million years up to 100 degrees C per million years. And that's pretty much spanning most of the reasonable rates of geological processes. So you can see, for instance, here it's about 40 degrees for this closure temperature at a rate of 0.1 degrees per million years. If you go up to 100 degrees C per million years, you've got a closure temperature that's about twice as high. So the effect can be significant in terms of, if you want to link a certain depth to where 40 degrees C is, or to where this closure temperature is, it makes a difference whether you're looking at a quickly cooled sample or one that cooled more slowly. And just to give you another example of kind of higher temperature system, this is argon inside hornblende. And you can see that as you go to higher temperatures, you also get a larger range for this effect of the cooling rate. So here you're below 500 degrees for slow cooling, and then for fast cooling, you're at nearly 600 degrees. So the cooling rate will make a big difference. And you'll see that actually in the exercise that we do for this week. You can play around and explore the cooling rate effect. So that's the essence of the thermochronology concept and the isotope systems we have left kind of blurry for the moment. There's some more slides about that we can discuss briefly, but I'm not going to go through in much detail because I think it's not necessary in this context. But do you have any questions at this point about the general idea here? Is the distinction between this like thermochronology versus geochronology clear? I see one or a few nodding yeses. Okay. If it's not clear, I'll give you an opportunity to ask some questions afterward. Maybe it'll become more clear as we go through the rest of the slides in this part of the lecture. But it's a new concept, and I understand if it takes a little bit of time for it to kind of sink in. It took me some time when I was a student as well. So then, turning to the question of what causes cooling, this is something that maybe has been a bit in the back of your mind as well. So we have the idea of this closure temperature that's just been defined, where we can think about the point where this mineral begins trapping the daughter product. But the question of what causes cooling is an important one. And there's a few different things that can cause a rock parcel to cool over timescales of millions of years. One of them is erosion. So if we have here my geophysicist representation of the Earth's topography and a kind of cross-sectional view, some crustal block here. So here's some mountains, and then the crust underneath these mountains. We know even from the earlier exercises that there are various erosion processes that are going to be interacting at the Earth's surface. So there's rivers that are carving valleys, glaciers that are flowing down, doing the same kind of thing at a different process, but forming valleys as well. And then there's things like landslides or hill slope processes, including those that behave like a diffusion process, like rain splash and other things like that. And all of these are basically removing material at the Earth's surface. So you can see if you just stand on the side of a river, I don't know that you'd see so many here in southern Finland that you can actually see sediment moving downstream. But if you are in a place where the river is moving a little bit more quickly, you can often just stand there by the side and you can see sort of sediment grains moving downstream, being transported away. And that's basically removing bedrock at the surface and transporting it downstream. What this does as a process overall and over long time scales is it basically removes overlying rock and causes the rock underneath to move upwards. So if we consider in this case, our reference frame is just the surface elevation not changing. In essence, if the surface is kept at a constant elevation and there's erosion happening, that means that rock underneath is continually being moved up toward the surface. Now, the rates of this process can be pretty slow. It depends really on where you are. In mountainous regions, these processes are a little bit faster. Here, the amount of bedrock that's been eroded in the past several million years is probably relatively small. It might be tens or not even tens of meters of bedrock that have been eroded in the past few million years. If you go someplace like an active origin today, over that same time period, you may have kilometer or even 5 kilometers of rock that's been eroded away in the last million years or few million years. But in essence, the idea is that the erosional processes are removing material at the surface, and there's rock coming up from depth continually all the time. This process essentially means that the rocks that are down here deeper will gradually make their way up to the surface, following, for instance, some little pathway like these arrows here. So you go collect a rock sample at the surface, but maybe 10 million years ago it was somewhere down here deeper below the Earth's surface. And of course, when it was deeper down in the Earth's surface, or below the Earth's surface, it was also warmer, and so it cools as it comes up to the surface. And this is probably the most common type of thing that you'd measure with thermochronology, is this erosional exhumation. So bringing rock from depth up to the surface as a result of erosion. This can happen basically in any tectonic setting, whether we've got convergent, extensional, strike slip, or completely inactive tectonic settings. This erosional exhumation happens in all of them. I mention that specifically because that's in contrast to tectonic exhumation. So tectonic exhumation occurs as a result of fault movement, by the fault movement alone with no erosion. And this happens mostly in places where you have extensional faulting, So just as a result of the fault moving, you have exhumation of the footwall, so the lower block in this fault model. So when the fault slips, the rocks basically come up and get exposed at the surface without any erosion happening at all. So this is limited to extensional settings, more or less. It can happen in strike slip settings in some places as well, but it's mostly happening in extensional settings. And often, if you're uplifting the surface when you do this, so there's places like in the western US, the Basin and Range, where there's active extension, and there are nice mountain ranges that are being formed there. When you uplift the Earth's surface, of course, you also get some erosional exhumation in combination with this tectonic exhumation. So these are different ways in which rocks can cool and come up to the Earth's surface. Of course, there are other things that can happen as well. You can have emplacement of igneous bodies, so some kind of volcanic deposits or whatever. The applications of thermochronology in these cases are generally pretty limited because the ages are going to be very similar to the geochronological ages that you would calculate. So it's often not really beneficial to do analysis for thermochronology in cases of igneous intrusions. Dikes and volcanic deposits cool pretty quickly, so the geochronological age is basically going to be the same as what you would get from thermochronology. And you can also have cooling following reheating. So if you have burial and then subsequent exhumation of sediments in for instance, foreland basins. So as active mountain ranges are growing, often they have a basin out in front that will eventually be incorporated and uplifted. And so you have this kind of burial and exhumation process happening in those settings. So there's some other options. All right, so let's now talk just briefly about some of the math here. It's not going to go into great detail, but just the general equations here in case you're interested. So if you want to calculate an isotopic age in general, so for some geochronological system, these are the pieces you need. Essentially, you need to know how much of the daughter isotope you have. So that's Nd in this case. How much of the parent isotope you have, Np. And then lambda is the radioactive decay constant. It's related to the half-life. So perhaps that's a bit more familiar, but this is basically just how frequently the decay is occurring. And if you have both of these things and you know the decay constant, you then can figure out from this how long it would take to produce that much daughter isotope and get an age directly from that. So that will work for geochronological systems, doesn't work for thermochronology because there's this problem of diffusion of the daughter product in some cases. So for that, we need to do something a little bit more complicated. We have to deal with solid state diffusion. So here comes yet another example of the diffusion equation. And in this case, generally speaking, the daughter products from for thermochronology are things that are not really incorporated in the crystal lattice of the parent crystal. So the host mineral is perhaps a better way to say that. So these can be things like helium and argon that are both noble gases, or other things like damage trails that just don't kind of nicely go into the crystal lattice. But these isotopes, as a result of not incorporating themselves in the structure of the crystal, will tend to diffuse out of it over time, and the rate of diffusion will depend on temperature. So we can use a diffusion equation for this, where we would say that the rate or time sort of change in concentration of the daughter isotope here is equal to the diffusivity. So this is the temperature-dependent diffusivity, so that's what we'll come to in the next slide, times the curvature or the second derivative of the concentration of the daughter isotope plus some production function P, or the production rate P. So you can see kind of a picture here in general of what this looks like. You've got some kind of decay process happening here, and you're producing helium nucleus or helium nuclei in green, for instance, here within a crystal lattice that looks perhaps something like this. And the parent isotopes in this case are things that are incorporated in the crystal lattice. The daughter product is not. So as I mentioned, to deal with this in terms of diffusion, we have to do this temperature-dependent diffusion. So that means we need to come up with a diffusivity D that's a function of temperature here. And much like the way that we looked at things like the change in rock strength with depth, where it exponentially decreases as you go deeper into the earth, we can do the same kind of thing for looking at the diffusivity of a daughter isotope within a crystal. Here, the difference being that the diffusivity goes up, so it becomes more likely to diffuse out of the crystal as you go to higher and higher temperatures. So we have some value here, D naught, that is the diffusivity at infinite temperature. I believe this is something that can be calculated, but I don't recall exactly where that comes from. A is the diffusion domain, so typically that's taken to be the size of the crystal that you're looking at. EA is the activation energy, so that's how much energy is needed to get the diffusion process going. R is the gas constant, and then T, K is the temperature in kelvins, so that's just my preference to put it the lower, like subscript K, to indicate that's the temperature in kelvins, not Celsius. So yeah, this is our temperature dependence here, and if you were to plot this equation, it would be an exponential, as you can see clearly. And that would show us that as we go warmer and warmer, rate of diffusion goes up, and that's why at high temperatures the daughter isotope is not retained in the crystal. And so, yeah, that's basically how the system is working. It's diffusion with the temperature-dependent diffusivity. So we saw for the stream power erosion law, we had advection with this advection equation where the constant for advection was basically changing as a function of where you were along the river channel. Here, our diffusivity is changing as a function of temperature. So just to show you a couple other things here that relate to this closure temperature idea. These are plots now of temperature versus time, and then showing on the lower plot, the corresponding daughter to parent isotope ratio over time. So as you go to low temperatures, essentially you expect to see this daughter to parent ratio form a one-to-one line, or at least a line of a constant slope. But at very high temperatures, you essentially see that there's no daughter product accumulating, so the daughter to parent ratio is going to be near zero. There's a couple other temperatures that are defined on here, the open and blocking temperatures. So these are the temperatures that correspond to the totally open, so everything that's produced diffuses out at temperatures above this TO, so I guess it's shown here. And then TB would be the blocking temperature, where every isotope that's produced is trapped inside the crystal. These aren't so important, but you can see, for instance, here where this closure temperature fits in this curve. So we approximate this curved behavior where you sort of gradually transition from trapping none of the daughter isotope to trapping all of it. We approximate that as basically a straight line with the closure temperature assumption. So yeah, as mentioned, already we've seen this closure temperature idea. What was done in this paper when the idea was proposed in general was to basically come up with a way of directly calculating this closure temperature as a function of this temperature-dependent diffusivity. The math is shown here. You'll see it in the exercise as well, but basically here you can say that the diffusion constant is a function of time is equal to the diffusion at time 0 times e to the minus t over tau. And tau is some time that's taken for the diffusivity to decrease by a factor of 1 over e. This, maybe we don't need to spend a great deal of time on here. I don't think you necessarily need to. You don't need to use this to complete the exercise. It might be useful to look over this slide and the next couple slides for the final report, just so that you understand what this Dodson equation is doing, because we will use that in the exercise. But you don't need to put the equation in or modify it, so I will keep it brief here because I think it's not a place where we need to spend a great deal of time. Anyway, it's an approximation that allows us to to estimate what the closure temperature should be without having to do the actual calculation of the diffusion, which is a little bit more involved. So there's a way in which we can calculate what this tau should be, and the tau is essentially going to be equal to gas constant times the closure temperature squared divided by the activation energy times the rate of cooling. So you can already see here the cooling rate coming into this tau, and once we have tau, we can then calculate what this closure temperature would be. This is basically just substituting things into the different equations, and I would encourage you to do that on your own if you're interested, just to see how all the pieces fit together. But what you can see here is that we end up with something where we have Tc, our closure temperature, as a function of the different things we can potentially know for a given mineral system: activation energy, diffusivity at infinite temperature. There's a geometry factor here, diffusion domain, and whatever else. And then tau is in here as well. So I mention this only because we have tau in this equation here for calculating closure temperature. The equation up here for tau has the closure temperature in it. So this is a system that normally you have to solve iteratively by calculating first a value for tau, plugging it in here to get a value of the closure temperature, and then going back and calculating what the closure temperature, or what the value of tau would be with the new closure temperature. And you iterate on that 4 or 5 times, and it converges pretty quickly to give you a value of closure temperature that's not changing. So it is a system that is not linear, because we have dependence on different parameters in both equations. Okay, so in general, what we would do if we were going to solve Dodson's equation, as you'll see in the exercise for today, is you define some constants. These are basically material properties for the mineral system we're considering. Put in some initial guess for the value of tau, and then go over some range of values and iterate for the values of tau and the closure temperature. So calculate a new closure temperature with the current tau, calculate a new tau with the new closure temperature, and then do the same thing a few times until you see the value is not changing. And you'll see something similar in the exercise for today. If you do that, essentially what you can do is end up with plots like this that shows, for instance, the cooling rate from 1 to 100 degrees C, and the closure temperature for this apatite system with helium inside the crystal, going from about 60 degrees up to around maybe 90 degrees at 100 degrees C per million year cooling rate. And so you can easily see the effect of this cooling rate on the closure temperature with this equation for calculating closure temperature using Dodson's approach. And just to link things up and kind of, I think this is almost the last slide here. So once we have the Dodson equation, that's what we use in the exercise, for instance, this week. We can calculate our closure temperature as a function of the cooling rate, and then we need to somehow link that temperature to a depth in the Earth, because we have only temperature at this stage. There's a few different possibilities. So one is you could just assume temperature increases at a constant rate with depth. So say it gets 10 or 15 degrees C hotter per kilometer. And that's one possibility. But I think we can do better than that. And that's what we're going to look at in the exercise for this week. So I'm going to stop here. And yeah, are there any questions? Okay. If not, let's take a break for just a second. Yeah, why don't we take 5 minutes and come back, and we'll do the second part of the lecture. I just need to answer a phone call quickly, unfortunately, somewhat urgent. So let's take 5 minutes and then we'll continue. Okay, folks, let's let's continue here. So, as I mentioned, there's some slides that we're not going to go through in much detail. These like parts 2 and part 3 that are kind of online only, and for those, this part 2 is basically about low temperature thermochronology. This is the description of a few different mineral systems, how they work, what the temperature sensitivities are, and things like that. These are kind of details that are useful when looking at the ages you'll calculate in the exercise, because the exercise we're going to do some age calculations. And also for the final report, it's useful to look through these slides. We don't need to go through them in much detail right now, but essentially there's 3 different age systems that are quite commonly used that are described here. So helium dating, which is helium accumulation inside of a parent or host mineral. Fission track dating, which is when fission occurs with uranium and damages the crystal lattice, the track that's left behind can be used as a dating method. And then there's argon, which works similarly to helium in the sense that it is a noble gas accumulating inside of a crystal and it's trapped inside there. Commonly used for dating micas, but can be used in other systems as well, like feldspars. So you can see here, for instance, the different mineral systems and their temperature sensitivities, and as well this kind of what the low temperature refers to in terms of absolute temperatures. Generally, it means temperatures below 300 degrees, although this biotite and muscovite systems can often be still included in low temperature thermochronology, or at least they're on the border. But basically everything that has to do with uranium or thorium decaying to produce helium, that's all low temperature thermochronology, as well as many of the fission track based systems in apatite, zircon, or titanite. So there's some slides here that describe these things. For example, here showing things like the decay chains and other things about how much helium is produced in the age equation, and various things about details of the different methods. So you're welcome to look through those slides and see how these different age dating systems work. I would definitely encourage you to do that. Those will be available on the course web page at some point later this morning. Another set of lecture slides that will also be available on the course page have to do with this idea of quantifying erosion using thermochronology. So how do we use these ages to go to getting rates of different erosion processes or cooling processes? There's some definitions in here that can be useful, and then some examples of ways in which we can calculate temperature, and then from that temperature calculate what exhumation rates would be and things like that. So I think I will just kind of leave it at that for right now. This is maybe not as relevant for the exercise today, but could be useful for the final report. So again, it would be maybe a good idea to just look through those slides and get a sense of how these different dating systems can be used to give us some information about rates of erosion. All right, so the one thing I do want to spend a little bit of time on here, and I may go a little bit quickly through this, but it's still useful, and that's about the final report for the course, which is essentially a combination of exercises 6 and 7, and then some kind of additional text related to the geology of the area where the age data are coming from. So in this case, we've got age data from the Himalaya of Bhutan, so nice looking place. And we're going to take ages from a paper published in 2014, where a number of different rock samples were collected in the western part of Bhutan as well as the east. We're only going to use the data from the west, just because we'll keep it a bit easier to deal with that way. But the samples that were collected here in this case were data for various different thermochronometer systems. So there's the uranium, thorium, helium system in apatite and in zircon, as well as fission tracks in apatite and zircon. We're going to basically only use the helium data because that's there's more of it and it's a bit easier to use. But you can see, for instance, here in this area in, you can see that we're in the western part of Bhutan, but this is the eastern part of the Himalaya as a whole. So we're over here. And we're going basically from the foreland basin, so out in front of the Himalaya, up into the high part of the Himalaya. And all the dots here refer to locations where rock samples were collected and dated and then analyzed in this article. The age data looks something like this. So this is now just shown as a kind of plot of the age versus the latitude at which the samples were collected. Since this is more or less a north-south transect, the latitude's a pretty good way to project the data here. And you can see also the elevations. So mean elevation shown with a kind of thicker black line, and then the deviation in elevation. So this is maximum and minimum along some swath. I don't know how wide it was. It's plus or minus 1 sigma. So actually maybe that's not a swath of elevation, but that's just the standard deviation. So you can see there are some interesting age patterns here for the different mineral systems, that ages are very young in the south, and then they get a bit older, and then sort of gradually get younger as you go further to the north. And then they have sort of youngest ages here in the sort of areas where there's the most relief or most like largest values for the standard deviation in elevation, and then ages maybe get a little bit older as you go further to the north there. So this is a complicated data set. Looking at the plot here, you can't necessarily easily look at this and say, oh yeah, well we can come up with an exhumation rate without much thought. It does take a bit of interpretation for an age data set like this. So that's what we're going to do with our last 2 exercises. So as mentioned, we look at a couple different processes that can be responsible for getting rocks up to the Earth's surface, but erosion is essentially the way in which rock is exhumed or brought from depth up to the surface. It might be related to tectonic activity, but erosional processes are basically responsible for getting rocks up to the surface in places like the Himalaya where there's convergent tectonics. And if we look at an example here, just to show you, let's say we had an apatite uranium, thorium, helium age of 12.3 million years. So this is an age that was measured in a sample that was dated based on the amount of helium present in the crystal and the time it took to produce that amount of helium. If we assume a normal closure temperature of around 75 degrees C, this is just a sort of typical value for the closure temperature, and a typical geothermal gradient of 20 degrees C per kilometer, how would you find an exhumation rate from this? So what information could we use here to come up with a rate of exhumation for this rock sample? So do you know, first off, when I say an exhumation rate, what you're looking for in general? Like what would the units be of an exhumation rate? Distance per time, right? Could be kilometers per million years, millimeters per year, centimeters per year, whatever, something like that, distance per time. So we have time in the age that we have here. We know that's how long it took for this rock to be exhumed. So we need to know the distance. How do you get the distance here?
Using gradient?
Yeah. So if we got a temperature gradient of 20 degrees C per kilometer, let's assume it's 0 at the surface just because it's probably close to 0. So how far down do we need to go to reach 75 degrees with the 20 degrees C per kilometer geotherm? Almost 4, right? So 3.75. That'll get us to 75 degrees C because 3.75 times 20 is 75. And so then if we have that distance, 3.75 kilometers, and it took us 12.3 million years to get there, so we've done that part. What you do is you just take the distance divided by the age that you have, and that gives you an exhumation rate here of 0.3 kilometers per million years. It's the same as 0.3 millimeters per year. The units work out to be equivalent in that case. So that's why you often see these two as the most common units to report things like exhumation rates. So that's a simple example. The issue is that, well, typically geothermal gradients don't increase at a constant value with depth, especially in active tectonic settings. The gradient will change with depth. So there's this kind of bending effect that's often expected as a function of the advection of heat. And so it would be better, instead of assuming a constant gradient, to use a 1D thermal model to calculate what the temperature should be as a function of depth, and then take the approach that we've done there for calculating the exhumation rate. And you could do that exact thing that we just showed as an example with a 1D thermal model. That's more or less what we're going to do in the exercises here. So we're going to calculate, for instance, a geotherm that might look something like this. This is at steady state, but whatever. Just an example, but you can see it's curved. It's not a straight line. And so depending on how deep you go down, that's going to affect your estimate of the rate of exhumation. And when we look at these active tectonic settings, advection is mainly what's responsible for bending the geotherm here. And that's the thing that tends to be the most important thermal factor in affecting the temperatures with depth. So heat production can be important, but advection tends to be the thing that's kind of dominating in areas that are experiencing fairly rapid erosion and exhumation. So once we have this thermal history, we then need to link that thermal history. Well, essentially we need to use that thermal field to calculate a thermal history for our rock sample. So if we've calculated that this is how the temperature should change with depth, if we start with a rock that's down at 50 kilometers depth, we basically can go along, in this case, at steady state, following this line and say, let's move up 1 kilometer each, whatever the rate is of exhumation. But let's say we had a rate of 1 kilometer per million years. So every million years, we would get 1 kilometer shallower and say, what's the temperature now? And record that to give us a thermal history. That's essentially what is shown, for instance, here. So if we start down at some depth here, at some time 1 and depth 1, we can calculate what the temperature is here. Some later time, it's going to be cooler, it's going to be shallower. We can calculate what the temperature should be at this depth, and so on as we go up toward the surface. And this is basically just saying that we, have some advection velocity Vz, and some time that'll determine how big these steps are in terms of how much shallower the rock position is over time. The result of this would be that in the end we would have a temperature history. We would know what the temperature was of this rock at different times back in the past, and we can then use that to calculate a thermochronometer age, because we can calculate things like the cooling rate, so we can use this Dodson's approach to give us a thermochronometer age. And finally, once you have the age, then we're going to do the same kind of thing that we've done in the earlier exercises, and that is use this chi-squared equation to compare our prediction to the observed ages from a data file. And we'll go through a process where you basically calculate what the age should be for a different thermochronometer systems compared to the age data that we have, and then maybe change the rate of advection to see if you can get a better fit to the data with a faster or slower advection velocity. And you'll do this until you observe I should put good fit in quotation marks here, because you won't get a very good fit in terms of the chi-squared value. It's not going to look very nice, but the best fit that you can get with the model that we're using. So that's all kind of perhaps a little bit abstract. Let's take a look here at the exercise. Let me just take a quick look here at the course page. I think we've covered everything up to the exercise at this point. So maybe we'll go through this, and then I'll see if you have any questions about this exercise 6. It might be a little bit confusing at the moment, but I think the exercise will help clarify things a bit. So yeah, This week and next week, we're on to talking about thermochronology. We won't deal with the age data this week. We're just going to deal with how the model works for predicting the ages. So we'll go through step by step and see how that model works. And then next week, you'll do some comparison to the ages. In terms of the coding, I think this is pretty light this week in the exercise. Like, you really don't have to do a lot of modification of the code. In part, that is because I don't want you to spend too much time with that, because with this final report kind of on the horizon, it's good that you have a bit of extra time to be thinking about that. And you'll produce a whole bunch of plots in this exercise, and I would say that you're welcome to use those in the final report in places where you think that would be useful. So that's a good thing to have in mind, because that's part of the point of exercises 6 and 7, is to give you kind of this pool of plots that you can take things out, and when you want to show an example of how your code works, you've got some ready-made examples of the plots it produces. So the first part, yeah, as I mentioned, is basically just about how this thermochronometer age prediction model works. And well, we can start with this guy. So this is our temperature equation. Lucky for you, you don't have to code it, because this would take a little while to make sure all your parentheses are balanced and things like that. It looks kind of nasty. It's not that bad, but there are some things in here that are a little bit unusual, like the complementary error function that we've not dealt with. And the point here is not really to make you waste a bunch of time balancing parentheses, but just to understand that this is the equation that's being used. And this is still a pretty simple scenario. So this is for time-dependent temperature calculation for a constant rate of advection. So a constant uplift rate, if you want to think about it that way in terms of a geological process. A constant rate that mass is moving up toward the Earth's surface. Starts out with a straight line initial geotherm, and then calculates the temperatures as a function of advection and diffusion after different amounts of time. So that's what the equation's doing. And as I mentioned, you don't have to worry about coding that, because it already is coded for you. As well, this complementary error function I just take from the SciPy library, so that's not anything to worry about there either. You have that stuff available to you. I think this link works. I should make sure it does. Yeah. So there's some notes here about solving the advection diffusion equation that might be useful, but you don't really need to. It's mostly just if you don't want to understand kind of what the code is doing. So at the beginning, there's a few cells that you just need to run. There's basically our kind of typical setup stuff: load some modules, set up the plotting. This temperature function is there, so that's the temp1d function, is basically just this equation here that already exists for you. And then there's this massive age predict equation, or function rather. It is not small. I don't know how many lines the function is. It's probably 150, maybe 200. You don't have to do anything to it, really, or you don't have to do much, but you do have to read through it and just try to see like what the different sections are doing. So all of the different things that are going to happen in the code, from calculating temperatures to predicting the cooling ages, all of that happens inside this one function. And you will go back in the exercise and do some things like add some text to a plot. That'll involve modifying this function. You'll see it's not super scary stuff that you have to do. But a good starting point is to actually try to read through and just see if you can follow what the function is doing in different parts. This could be split off into a whole bunch of other functions, but that means then you're going to run like 10 Python code cells instead of running one. So I just kept it all in one place. It's a little bit clumsy because it means it's really long, but all the stuff that needs to happen here, like setting up the thermal model, how deep are we going to do these calculations of temperature, how many depths are we going to calculate temperatures at, all that stuff is done here. All of the parameters for the different thermochronometer systems are prescribed in here. So like activation energy, the size of the crystals, D naught, this diffusivity at infinite temperature, all that stuff is listed here. You don't need to modify those things. There's the gas constant. And there's some unit conversion. Like you'll see a lot of the lines that are in here are doing kind of simple things. So you can probably read through the comments that are in here and get a pretty good sense of what the different parts of the code are doing. There are some things in here that are a little bit more complicated, but not anything where there's really nasty logic or anything. I think you should be able to follow most of it. It just make sure you take the time to take a look. In essence, what it does is defines a whole bunch of constants, calculates temperatures. So this for loop here is going to go through and calculate temperature at a whole bunch of different times. And as it's going through and calculating the temperatures, it's also saving a temperature history for some rock parcel. So it says, for instance, if your advection velocity is 1 kilometer per million years and you run the model for 10 million years, it will start out with the rock down at 10 kilometers depth and calculate what the temperature is at time 0, and then move up toward the surface and record the temperature history as you go along up toward the surface. Then it uses that temperature history to go through and calculate what the thermochronometer age should be based on that temperature history. So you can also see that is in the code. And then in the end, it does some plotting. And if you ask it to, it will calculate the different thermochronometer ages and can print those to the screen. And you'll end up adding a couple lines here to have those values show up on your plot. So as it is, once you read through this and understand at least a bit of what it's doing, you can go here to part 2, and that is basically just to run the code, and you'll produce a plot that looks like something, well, actually it should look exactly like this when you run the age predict function by itself at the start. So here it produces a calculation of the temperature from 0 down to 50 kilometers depth 50 million years ago. So watch out here that I'm using MA in this case to refer to millions of years ago. So this is the starting temperature in blue, and then the temperature at present day, so 50 million years later, is shown in orange. So just be careful with the units there. It's with a thermal model, I would be tempted to start at time 0 and then run 50 million years forward. But the problem is when we want to compare this to age data, it's easier to have it in the context of like what the temperature was 50 million years ago versus present day, because all the ages are going to refer obviously to time in geological past. So if you run the code, it produces this plot already, so you don't even have to worry about making any changes to that. But you do have to go here, and the first step is to like add some axis labels, add a title, and then also add some text on the plot that shows what the rate of advection is, or so what the kind of uplift rate would be in the code. Once you've done that, so you can do that here, and I'll note that you should say, for instance here, the age output equals the function call. The function itself, if you look at it here, it returns 6 different values. If you need to refer to any of those, it's helpful to say that, you know, age output equals age predict, so the name of the function, and then all of these different values will be stored in this age output variable. That's used also to check and see whether the code works the way it's supposed to. So you'll see there's examples here like age output equals none. You should replace that with your function call. And then you'll have some tests under here that will check to see whether you get the right results. So it should be obvious if you've done that wrong. And so just pay attention. So you make a plot, add a caption, and then there's a couple test cells underneath there just to make sure that you did the right thing. After that, then it's essentially just playing around with the code to see how it works. So you'll change things like the advection velocity, make the advection velocity faster. How does that change temperatures? Make the advection velocity slower. How does that change temperatures? Essentially just getting some ideas of how this code operates. So I don't think you actually have to modify anything in the code here. You just have to call the function with the different advection velocity. And you need to go look at how the function is defined to see how you change the advection velocity. You shouldn't change it in the function itself. It's a parameter that you can specify when you use the function. So that's what's going to happen with that. Then you'll change the simulation time, same kind of idea, just changing a value when you call the function to get a different, in this case, 100 million years of time instead of 50 million years. And then you have an opportunity here to calculate the temperature for a really long time and see that the code is not infallible, but you'll get these kind of, well, spectacularly high temperatures if you run the code for long enough. So that's an important thing to think about because it's a limitation to how far you might want to go with this code in terms of stimulating temperatures. Then you can play with the thermal gradient as well. So this is just initially how much temperature increases with depth. So you're sort of told to vary that. And then lastly, there's an option to predict temperatures at different times. So like we saw here in the plot, the temperature at 50 million years ago and 0 MA, but you can also have a number of different temperature calculations in between there. Can help you to see how the temperature changes over tens of millions of years. And so then you'll do that, you'll produce another plot that has different temperatures, and then you've got a few questions, and that's kind of it for problem 1. So already maybe you get the sense that the coding part is not looking too scary. For problem 2, we're using the same code basically, but now we're going to do the calculation of the thermochronometer ages, and this is using the Dodson's approach. So we have this thermal history I mentioned that gets recorded as the model runs, and then you can use that thermal history to calculate what the closure temperature would be for some rock that is cooling on its way up to the Earth's surface. Again, you don't have to put these equations in, they already exist. And so part 1 of the problem number 2 is basically just to run this cell that has these equations for tau. This is the diffusivity characteristic time, if you want to talk the talk. And then the closure temperature underneath that. And then there's some extra stuff in here just to make sure that you get a reasonable value for the closure temperature. But you don't have to modify that function. That's already there. You just have to run the cell so that the code can use it, because you won't be able to predict ages without running this cell. So then for part 2, I guess, which actually should be no, I guess it is part 2. Here you're going to run the code now with the option enabled for calculating a apatite uranium, thorium, helium age. So you can look again at the way the function is defined to see how to do that, but basically you just need to run the code with that enabled and then add some text to the plot that it produces to show what that age would be and show what the closure temperature is for that model. So you're even, I think, told, well, yeah, just to add the text to display those two things. So you will modify the function and then run the function cell again so that you update that, and then you should get a plot that shows what the age is. And of course, there's another test cell that allows you to see whether you get the right age. Then you do the same thing for the other 2 thermochronometers that are in the code already. So just same kind of thing that you've done, but adding text to display the other thermochronometer ages. And then the one thing that does involve a little bit more coding, and I still think it's not that much, but there's an option to visualize the thermal history. So I mentioned that like you record as the rock moves up to the surface what the temperature is. You can also plot that to sort of see what the temperature history looks like as the rock moves up toward the surface. But at the moment, there's nothing there for doing that plot. So in here, it tells you which data frame to use to make the plot, and all you have to do is just replace this pass with the function call to make a plot of the temperature history. And that should be hopefully fairly straightforward. And you should plot that as black circles, as is mentioned here, so you will have to set the style of the plot. It's typical pandas plotting, so I think this is something you've already done once before. And importantly, don't remove this if statement as part of the change. You should only change the stuff that's within the if statement, otherwise you'll break the function. So then, yeah, you make a plot that'll show the temperature history. That looks nice. Then you increase the advection rate and do the same kind of thing with showing the temperature history again. And then there's a few questions and you're done. So, yeah, speaking of questions, are there any? Okay. If not, I will make one very quick change to the exercise. Lotta noticed one small typo, so I will fix that, and then I can put the link to the exercise for GitHub Classroom. I'll put that in Slack. Then, unfortunately, I need to run because I need to go fill in for a meeting that's happening right now. But I think Lotta and Alexei will be here, so they can assist with any questions you have with the exercise. And if there's other issues that they can't answer, you're welcome to post questions in Slack, and I'll get back to it after 2 o'clock. So, yeah, if there aren't any questions, I'll stop here, quickly make the updated version of the exercise, and you guys can get started on that.